Okay, so this problem wants us to determine the shear force and bending moment as a function of x, and I've defined x. Most of the time, I'm going to work my problems with the variable x starting at the left and going to the right, pretty much every time. There may be an occasional problem where there'll be a benefit to have a different origin or even go in a different direction. But typically, I'm going to always try to go left to right, unless we come up with a different approach. Now, in this particular one, let's talk about this for a second. Looking at the loading on the structure, is it continuous across the whole beam?
It is.
Yeah, if you look at the loading, it's just linear, right? That's a function. You could write that as a single equation. So we'll be able to write a single equation that's valid for the whole structure for shear force and bending moment. What's the starting moment in shear force at A? Oh, we're going to have to find that. What's the ending shear force and bending moment at B? 0. It's a free end, so there's going to be no shear, there's going to be no moment. Unless there's a moment applied at the end, but I don't see an applied moment. Unless there's an applied force at the end, and I don't see an applied force. That's a distributed force. So we're going to need to find the shear force and bending moment at A, and we'll use those as our starting locations. So let's do that first. So what I'm going to do is I'm going to assume positive shear force at A. Now, on the left-hand side like that, would positive shear force be up or down? It would be up. So this is not a reaction. This is actually the shear force at A. It is a reaction, but now it's a specific one. And also I'm going to assume positive bending moment at A. So I'm going to use the little plus sign at the top to remind you that those are both positive signs. So I'm going to find those by doing a free body diagram of the whole structure and use my equations of equilibrium to find them. So how are we going to handle this distributed load? What do we usually do? Yeah, we'll turn it into an equivalent concentrated load and at the centroid. So what would be the equivalent concentrated load of a triangle? It would be 1/2 base times height, which looks like it's going to be 20 kips. And the centroid is 1/3 from the big end or 2/3 from the small end. I think either way, 1/3 of 20 feet here or 2/3 of 20 feet. So I'll do it that there. So I'm not going to write the fraction. So 2/3 of 20 is 40/3 feet. 40/3, 2/3 of 20, right? All right, so let's go ahead and find those reactions. So now I'm going to do my equilibrium equations. And when I do my equilibrium, I like to use right-hand rule for my moments. So I'm now going to sum my moments about point A and set it equal to 0. So with right-hand rule as my sign convention, what kind of moment is this at A?
Negative.
It's negative. About A, my concentrated equivalent force is going to create what kind of moment? Positive or negative? Also negative. So it would be negative moment. The force is 20 kips. And the distance is 40/3 feet. Anything else? Well, the shear force doesn't create moment about A. It passes through A. So that's it. So I can find my moment at A. What is my moment at A? It looks like it's going to be negative. And whatever 800 divided by 3 is, that should be 266.7. And that'll be kip feet. So you can see we're going to start off with a negative moment. What does that mean, negative moment? Well, I assume what kind of moment here at A? Positive. So what kind of moment, what kind of bending moment do I have at A? Negative. So now I'm going to sum forces for equilibrium. And when I sum forces in the y direction, I'll just assume up for my accounting is positive. So looking at all the forces, I've got this shear force is up, so that's positive. This a concentrated equivalent 20 kip load is down, so that's negative. And that's it. So it looks like my shear at A is 20 kips. So what's the shear force at A? It's positive 20. So now I have a beginning. So any questions about that? The only difference between here and any other problem we've worked is I'm actually calling these shear force and bending moment, not just a force in a moment. They're specific forces. So now I'm going to make a cut. So I'm just going to kind of, just for the time being, just to talk about it, I'm going to...
I got a question.
Yeah.
So when you assume the bending moment at A at the very beginning, you drew it clockwise and then clockwise?
Well, this is a positive bending moment, right? It's going to make this part of the beam try to smile. It's going to make it bend up, right, into a smile. I always assume when I make a choice for shear force and bending moment, I always assume positive. But when I actually sum equilibrium, which is a completely different coordinate system, I always do right-hand rule. So under right-hand rule, that's negative. Negative moment, even though it's a positive bending moment. Confusing, but bending moment has a sign convention. Just summing moments does not. You choose. But bending moment has a sign convention. And you're stuck with that. Yeah.
You wouldn't have to call those shear and moment in this problem, would you?
Well, I'm writing equations for shear force and bending moment. I want values to match my equations.
Like you would know that it's the moment that's at A. Like
It's not the moment. We're writing an equation for bending moment and shear force. We're not writing an equation for just moment. Because then you could have positive signs and I could have negative signs. And who's right? But now we have a common way of communicating. If I say bending moment, you don't get to choose. There's going to be negative, and it doesn't matter which direction you choose for doing moments. Negative is negative. If it's negative, it's negative. It can't just be positive because you say it is. It's like the same thing with compression. I think you have an easier time thinking about axial force. Tension's tension. You don't get to choose, right? It just is. So I'm going to cut this and do method of sections. You want to use the left side or the right side?
No.
Well, we do have these values, so that's to our advantage. We already have it. And also the left side is just a triangle, where the right side would be a trapezoid. And remember, we're doing this all as functions of x. So just to give you a little something to think about, up to that cut would be our x value. And what would this part of it be? Right, it would be the length minus x. So that would be 20 minus x. So all these areas would be functions of 20 minus x, which would be a little, not hard, but I think, more to keep up with than just looking at values of x. So I'm going to go to the left side. So I'm going to draw that again a little bit larger so we can see it, and then we'll write the equations. So now I'm looking at, here's the left side of my structure. And this is going to be at some distance x. And I've got a shear force acting up here of 20 kips. And I've got a bending moment acting here that is 266.7 kip feet. And then along here I have the load. All right. What's the value of that load as a function of x? Well, this is just a straight line. The equation of a line is ax plus b, right? What's a? The slope. What's the slope of this line? Rise over run. So the slope will be 2 kip per foot over how many feet? 20. So this is going to be a slope of basically 1/10. And then where does it start when x is equal to 0? 0. So this should just be what? Should just be x over 10. And you can check it. This function should tell you the value of the loading anywhere as a function of x. When x is 20, what should it be? 2. Put in x equal 20, what do I get? 2. When x is 0, what should I get? 0. And I do. So it works. Then I'm going to come here and I'm going to find positive shear, positive bending moment. Now, why did I choose those directions? Because that's positive shear and that's positive bending moment. Now what? Well, I'm going to come back and take this distributed force and break it up into a concentrated equivalent force. I'll call it F, and I'll say the distance is D from the cut. So what is F? What is the area underneath that curve? Well, it's a triangle. It should be 1/2 base, which is x, times height, which is x over 10. So 1/2 base times height. That's going to be x squared over 20. Can I check that? Yeah, we've done this before. If I consider x to be 20, we already figured out that the concentrated equivalent was 20 kips. What if you put 20 in here? You get 20. It works. What's the distance? From the cut to the centroid is 1/3 of the distance. What's the distance? X. So it'll be x over 3. So for me, there's your problem right there. If you can do that, the rest of it's just grind it out with your equations of equilibrium. But if you don't get this right, it doesn't matter what you do next, right? So if you're going to focus on anything, especially on the homework problems, on the exam problems, make sure you take your time to do this right. Because I'm going to give you the most credit for this anyway. And I'm also going to penalize you the most if it's wrong. So once that's done, all I have to do is say, okay, now I want to make sure this is in equilibrium. So we always like to sum moments at the cut. We've done that a few times. And we're going to do it again. I'm going to use right-hand rule for my sign convention for my moment. So starting here, what kind of moment is this with this sign convention? It's positive. The shear force does not create moment at the cut, so don't have to worry about that. What about this force F? What kind of moment does it create about the cut? Positive. So it'll be F, which is x squared over 20. So that's F. And then times the distance, which was x over 3. So there's my distance. So now I've accounted for the load. What else do I have? I've got this 20 kip force. How far is that away? X. And what kind of moment does it create about the cut? Positive or negative? Negative. So it'll be a force of 20 kips times a distance of x. Again, force times distance. And then right out here at the end, I've got a moment of 266.7. Now with this sign convention, what kind of moment is that? Positive. 266.7, and that'll be kip feet. So I just solve for the moment. So I'll come back and I'll say moment now, which is a function of x, is going to be equal to, I like to put this in brackets so I can put my unit at the end. So I also like to start with the biggest term and go down. So looking at this one, this is going to be x cubed over 60, and it'll go to the other side of the equation, so it'll be negative x cubed over 60, then plus 20x minus 266.7, bracket, my units are kip feet. So there's my equation for moment. Can I check that equation? Yes, I can. What do I know? What is the bending moment at A? We solved for it already. What was it? Negative 266.7. A occurs at what value of x? 0. So plug in 0. 0, 0. Hey, negative 266.7. It works. What's the bending moment at B? 0. That's at x equal 20. Plug in 20 here. You should get really, really close to 0. But you'll have to do that. I can't do that one in my head. Anybody getting close? You got really, really close to 0? This is an approximate anyway.
Yeah,
that's supposed to be 0.66666666666666666 as long as you want to go. But I decided to stop. Say 0.7. Okay? See how easy it is? So now the equation for moment, you can plot that and you can see how the moment varies from A to B. Can I plug in a negative value for x? Well, sure, it's a function. Does that make any physical sense? What would the moment be at negative 10? You'll get a value. It has no physical meaning. This equation is only good between x equals 0 and x equal 20. Outside that range, it's useless. So every equation is going to come with a range. All right, so now we'll do the next thing we need is shear. So we'll sum forces in the y direction and set them equal to 0. So let's see what we have in the y direction. So since I'm assuming up is positive, this force shear is down, so that'll be negative. My force F is down, that's negative. And F is x squared over 20. And what else do I have? Oh, this 20 is up. Is that it? I think that's it. So I'm going to solve for shear. Now it will be a function of x. And when I solve for shear, I get negative x squared over 20 plus 20. And that'll have units of kips. Do we know the shear anywhere? What's the shear at A? We solved for it already, right? It was positive 20. And A is at what value of x? 0. So plug in x equals 0. What do you get? Hey, you get 20. It matches. What's the shear at the free end, B? It looks like it's 0. And that's at x equal 20. You plug in x equal 20. Hey, what do you know? You get 0. It works. And while we're here, do you see any relationship between moment and shear? Think about calculus. Take a wander to Dunn Hall in your mind. Yeah, it looks like that if you took the derivative of the moment with respect to x, you would get the shear. Now, we haven't proved that yet, but I'll tell you, it's true. So here's another check. If you take the derivative of your moment and you don't get your shear equation, then something's not right. So you can only match each equation with things that you know about the structure, but there's a relationship between these two independent things. Pretty cool, huh? Now some people ask me, oh, I'll just do the moment equation and I'll take the derivative and I get the shear. You can do that, but you have now, as they say, thrown all your eggs into the moment basket. And if your moment is incorrect, well, your shear is incorrect. It is possible to screw up the moment and get the shear right. Hey, you got half the problem instead of getting none of the problem. So I would always do that and just use this as a check instead of something to lean on as a tool. Because if it doesn't match, then you have to decide, well, where did I make my mistake? Is my shear equation wrong or is my moment equation wrong? I would say probably you should check the moment equation because you can see there's a little more going on there. Distances to centroids. When you're summing forces, most people can usually get the area of a rectangle and triangle. They sometimes mess up the distance to the centroid. So it's more likely that you would make an error in moment than in shear. Okay? Any more questions about that one? That took 20 minutes to work.